So we would be talking about various parameters that actually defines viscoelasticity, and also we will discuss about the rheometric, or how we can characterize a viscoelastic material using a rheometer, and then briefly we will talk about the temperature dependent studies using oscillatory method. So after this session, we would have a live demonstration of the equipment where I will show you how we can effectively measure any particular sample using using an oscillatory test. Yeah. So the first question is, what is viscoelasticity? Now, if you remember in my yesterday's talk, I was mainly focusing on the viscosity measurement. Now, the question arises, whether can viscosity explain or characterize any sort of fluid or solid completely? Means, can it give an flow behavior as well as structural behavior of any particular material? Any or it can only give you a flow behavior of material and do not tell you about the structure. So mainly viscoelasticity or oscillatory measurement, when we talk about it, it gives you not only the flow behavior of your material, but it also gives you an structural behavior of your material. So for example, in case if you have a viscoelastic fluid, you know that it has some viscous part in it, and also it will have some elastic part in it. So when we measure the viscosity, we are only getting an information of the viscous part of that particular material. And when we leave behind the elastic part. When we talk about oscillatory studies or viscoelastic characterization, we not only consider the viscous part of any particular material, but also the elastic part. We'll come to know what are the parameters that define the viscous part as well as elastic part in any of the material. So before going deeper into viscoelasticity, again, I would like to show you a material spectrum. So as I have explained yesterday too, materials, and when I say materials, I am mainly talking about materials which you can physically see or physically feel. So those type of materials can be mainly classified into 4 parts. Materials can be ideally viscous, like water and oils. Materials can be viscoelastic liquids. That means liquids which has some form of elasticity or some temporary, I won't say temporary, but some form of structure present in them. The examples can be glues and shampoos. Then materials can be viscoelastic solids, which would mean that so materials can be viscoelastic solid, such as pastes and gels. These type of material predominantly have elastic structure, but under certain stress, or if you apply some force on them, at some point of time they will start flowing. And then materials can be ideally elastic, such as stone and steel. These type of materials usually follow an elasticity law, but these materials also are somewhat viscoelastic materials depending upon a certain criteria. So for example, if I increase the temperature of steel, after a certain point, it will melt and it will start flowing. So all of the material which is present in this world are mainly viscoelastic in nature. Although considering the ambient conditions, we can say that steel or stone is a elastic material, ideally elastic material. Now, when you come to rheometry, ideally viscous liquids and viscoelastic liquids can be characterized using a rotational test. Although in case if you want to do some sort of structural studies, means you don't want to know, in addition to flow behavior of these materials, you want to also to determine the structural property of these materials. Oscillatory test can be performed on all type of materials. So mainly when we talk about viscoelastic solids and viscoelastic liquids and elastic material, it is the oscillatory test that is much more suitable than compared to rotational test. Now, what exactly is a viscoelastic behavior? I suppose you have seen these examples, or probably in your practical life, or you have studied them. So in case if you don't know these effects, you can see over here on the left hand side of your picture, this particular effect is a rod climbing effect. What happens is when you steer a viscoelastic material, the material itself will attach itself to the steerer and it will climb up. And on the right hand side of picture, you can see something called as swelling or die swelling behavior. So here you would see that when the viscoelastic material comes out of any particular die, it expands. So this is a very common behavior in polymers, in case if you are dealing with polymer solutions or any type of viscoelastic material. Now, why these effects happen? This basically happens because of the elasticity present in these samples. So what happens in Weissenberg effect, that is the rod climbing, that when you steer that viscoelastic material very fast, then the direction of the normal stress which forms is in upwards, or you can say that the stress acts as a hoop stress. So when the normal stress, the direction of the normal stress is upwards, that means along the steerer direction, then the viscoelastic material climbs up. This particular phenomena is very common in polymer solutions. And when you go through online and see different videos, you would find a lot of videos showing this particular effect. When we talk about die swell is basically because of improper relaxation time given. So this is something which is a common issue in polymer extruding. So when you talk about improper die means improper die length, this type of effect comes into play. So if your die length is very small, means if it is not appropriate, then the polymer usually does, or molecular chains in the polymer do not get sufficient amount of time to relax. When they do not relax, when they come out of that particular die, then the molecules try to entangle and regain its structure. So you would have a swelling effect after it comes to the die. This is something which is you can say it is a issue in most of the manufacturing process of polymers, or in case if any application related to extruding. So why it is important to characterize viscoelastic material? Definitely materials can be extruded. So most of the times this is showing an example of polymers. So you can see these type of defects in polymer products like extruded swelling, which is basically an issue related to die swelling. Then you have shark skin effect after film blowing, and orange peel effect after blow molding. All these defects in polymer manufacturing is because of viscoelastic effect of a polymer melt. Now, in case if we don't study viscoelasticity of a material, these type of defects would be very much common for any particular industry. So it is really very important to know the viscoelastic property of that particular polymer melt or polymer melt blends. Another example can be food industry. Now, most of us, what we eat is viscoelastic in nature, whatever food product we eat. So mainly food products can be fluid as well as solids. Now, when we talk about fluids, mostly food fluids are non-Newtonian in nature. And when we talk about non-Newtonian behavior, it also somewhat resembles a viscoelastic effect. So then definitely, if it is viscoelastic, we need to characterize the flow behavior of these type of fluids, as well as we need to characterize the structural behavior. And then we can perform different sort of time-dependent studies and thixotropic studies. Same way, in case if we have some solid food product, solid food product do have a permanent structure, means very strong structure. So we need to study the elastic and inelastic behavior of that structure. And also we need to study the viscoelastic as well as plastic behavior of these solid food products. Now, why solid food product is very important for rheological oscillatory studies? Because it will give you an idea about mouth feel. So whatever we eat, how it will behave inside our mouth, whether it will spread thoroughly, or there would be some sort of I would say, means like unpleasant mouthfeel for that particular food product. Viscoelastic behavior can simulate everything. So, for example, in case if you are eating excessive amount of fat, you would find that the consistency of that fat product is very good. Although, in case if you are eating something having a bigger size particles, then the mouth feel what you will have would not be that good. So, in order to simulate how that food product is going to behave in your mouth, is somewhat related to viscoelastic behavior study. Now, what are the parameters that define viscoelasticity? So, first parameter is, of course, yield point. Yesterday, Dr. Muhammad had actually shown different various studies concerning yield point. So what this yield point actually is. Now, yield point can be defined as a limiting value of shear stress, or in simple terms, it can be defined as the minimum amount of stress that is required to plastically deform any particular material. Now, here you can see an image or a microstructure. So most of the solids do have the structure like this, means all the atoms and molecules are actually joined together. When we apply certain amount of force to this structure, at certain force, the structure breaks up. That particular force, or the minimum amount of force that is required to deform this structure, is called as yield stress. Now, if you see graphically, here you can see a plot in between gamma prime, that is shear rate and shear stress. And here you can see two examples. So first example is without yield point, and second example is with yield point. If you remember yesterday, I had spoken about Herschel-Bulkley and the Bingham model. So Herschel-Bulkley and Bingham mathematical model usually follows these type of curves. So here you can see in first curve, the graph actually starts from origin. So that would mean, so for example, if I measure a water sample, most probably, because water does not have any sort of elastic structure present in them, so most probably the curve would start from the origin point, and then move on move along with the applied shear rate. Although there are few viscoelastic fluids, or most of the viscoelastic fluids, whose curve do not start from the origin itself. So those type of fluids do possess some yield stress or some yield point. Now that yield point is given by the intercept of the curve. So for example, if for second material, you can see it starts from tau f, that is the shear stress. So tau f would be the yield stress of this material too. So Herschel, when I talk about Herschel, Bulkley and Bingham models, they usually extrapolate the curve and try to find out the intercept of that of the stress axis. So that intercept would actually give you the value of yield stress. So this is also one way to determine yield stress. Of course, there are other methods, other techniques, or other tests that can also give you yield stress of any particular material, but this is predominantly used when we use rotational methods to determine the yield point. Although this is widely used, but this is not I would say means like somewhat this is not a correct way to measure the yield point of any particular sample. I'll come to that, why it is not that much accurate and correct way to measure a yield point of any particular viscoelastic. Now, another factors or another parameters are modulus and damping factor. Now, in order to understand modulus, first we need to understand what is stress and strain in terms of deformation here. So again, we would consider two-plate model where our sample is actually filled in between these two plates. Bottom plate is fixed and we have upper plate moving. So now if you remember our yesterday's session, we discussed about the velocity and area. In this case, velocity is replaced by a parameter that is S, which is a displacement. That means for any sort of oscillatory studies, we do not rotate, or this upper plate is not continuously moving. So we are not including velocity as a parameter. What it does is this plate, moving upper plate, it moves to and fro. So that's why we are always considering a displacement, that is S, rather than a velocity. Now, if we define the force applied on the sample because of this displacement divided by the area of the upper plate, we will get shear stress, and which is given by the force applied divided by the area of this particular plate. The unit of shear stress is in pascals. And if we divide this displacement by the sample height, we will get the shear strain. Now this shear strain is a unitless quantity because here we are talking about displacement and height. Both had somewhat same units, so you don't have any particular unit for strain. It is a constant deformation or constant quantity. But for most of the strain studies or oscillatory studies, we always represent strain by percentage. In case if you have done any sort of, I would say, tensile testing, you would know means like that most of the parameters or that we actually decide for any sample to be tested is in percentage, that is a strain percentage. Same way, here also strain is represented as in percentage. Although if you are talking about a tensile testing, it is basically the force direction is in a is actually in normal direction to the load cell. That would mean you are elongating your sample. So that's why that type of strain is not called shear strain, and in this case we are actually moving or applying a force in a shear direction. So that's why we call it a shear strain. Now in this case, whenever we talk about a rheological measurement, it can be either stress control, where we control the stress and measure the strain, or it can be strain control. That is, we control the strain and we measure the stress. And the best way to measure any rheological sample is controlling the strain, that is controlling the deformation, and measuring the stress. Because in most of the cases, strain is somewhat a material or a motor quantity, means you can easily define a deformation using any particular electronic motor. And shear stress is mainly a sample quantity. So it is always better to control the strain and measure the stress rather than doing vice versa. Now, after defining this strain and stress, we would define a parameter called modulus, that is G star, given by stress divided by strain. So in any oscillatory measurement, we define strain and measure stress. Then the software automatically divides this stress by strain and give you a quantity called as G star, which is known as complex shear modulus. Now here we are dealing with shear modulus. In case if you are working on a UTMs, you would be talking about Young's modulus or elastic modulus. Or in case if you are working in a compression study, you would be talking about bulk modulus. Because here we are dealing with shear forces, so we call it a shear modulus. There is an empirical relationship between elastic modulus, bulk modulus, and shear modulus. And most of the times when you talk about any rheological study, you can, in case if you are doing some sort of solid testing, solid sample testing, you can always convert the shear modulus into elastic modulus. So there is an empirical relationship, and the unit of the shear modulus is given by Pascal. Now, physical meaning of this shear modulus is just the stiffness of any particular material. So for example, if I have a gel sample, if I compare a gel sample with a glue sample, I can easily say that the stiffness of gel sample is more than that of the glue sample. So that means gel sample do have a higher modulus compared to a glue sample. So most of the oscillatory studies, we would be dealing with this particular quantity, that is the shear modulus. Just to give you an example of a shear modulus and what it means, you can see here different example of different cheese products with different shear modulus. So we have a cream sample which is having a very low shear modulus. That means it is the hardness of this particular cream sample is very less. Although if you go to extra hard cheese, then the modulus is very high comparatively. Now this G star itself, when we talk about complex shear modulus, is a complex number and can be divided into two parts, which most of you would be like dealing with when you are doing any sort of rheological study. So these two parts can be G prime and G double prime. So here you can see G prime, and on x-axis is basically an elastic property of any material. That means it gives you the elastic nature of any material. And G double prime gives you a viscous property of any material. G prime is called as storage modulus and G double prime is called as loss modulus. Why it is called storage modulus? Because after deformation, the energy in the structure is stored and it regains its structure. So that's why G prime is always elastic, will give you an elastic property and is called as storage modulus. Although When we have G double prime, it is called as loss modulus, because when you deform any material and the structure is not intact, that means the energy in the structure is lost. So that's why it is called as loss modulus, and will give you the viscous property of any particular fluid. Now, again, in case if you divide this G double prime with G prime, you would get something called as damping factor. That damping factor is also very important parameter in order to define the transition of any particular material from solid to liquid or liquid to solid. As the formula suggests of that tan delta, that is G double prime divided by G prime, it primarily gives an information about the viscous behavior of any particular. So most of the times when you are doing any experiments where you are expecting some sort of phase transition, like curing experiment, or say in case if you are looking doing any type of time dependent studies, this tan delta factor would actually tell you what are the changes that is happening in the structure. So that is also something which is very important to characterize. Then again, we have something called as phase angle difference. So the phase angle difference is basically defined as the difference in the how your material is actually behaving under different deformation, and is also very crucial to determine how physically your material looks like, or you can say that how the structure of that particular material is how the structure of that particular material is behaving under different deformations. Another quantity that we can define using G prime and G double prime or G star, that is complex modulus, is a complex viscosity. So complex viscosity is also very important, especially when we deal with the polymer melts and viscoelastic solids. So if you remember yesterday, I mentioned that it is always better to do oscillatory tests on a paste-like samples, because that prevents excessive amount of wall slippage or removal of the sample from in between the geometries due to high shear rates, is because we can always determine the viscosity with oscillatory tests too. So here we call it a complex viscosity, and it is given by G star divided by the frequency of the oscillations. So when we will have a demonstration, I will show you different ways in which you can interpret eta star, that is complex viscosity. Now this is a very good illustration of how these oscillatory tests are being performed. So here you can see in the bottom figures, you have the fixed bottom plate, and top plate is moving at certain displacement. You have given certain displacement to top plate, and your sample is filled in between. Now, depending upon the properties of the sample, the behavior of the delta, that is the phase angle, would be different. Now, these oscillations can be considered as in sinusoidal waveforms. So here you can see this movement of the top plate is basically corresponding to a sinusoidal wave, what you can see over here in this figure. Now, when you input certain deformation to your material, the response that your material gives will define the property of your. So for example, and that phase lag means the lag in between the input signal and the output signal would give you the value of phase angle, that is delta. So for example, if your phase shift angle is 90 degree, that means your output signal is 90 degree out of phase of your input signal. You can say that your material is ideally viscous. So for example, if I measure a water sample, I would have something like this with a phase shift angle of 90 degrees. Now, in case if I am dealing with viscoelastic liquids like shampoo or glue, then the phase angle difference or phase shift angle difference would be, or the phase lag would be greater than 45 degrees. So I can say that yes, still I am dealing with viscoelastic liquids and my G double prime is greater than G prime. Now, as I have mentioned, G double prime basically gives you an information about the viscous part, and G prime would give you an information about the elastic. Again, if I am measuring some samples and I get a phase difference that is delta lesser than 45 degrees, I can say that these type of materials have are a viscoelastic solids. Here I would find my G prime, that is the elastic property, is dominant over the viscous property. Now, in case of perfectly elastic material, my phase shift angle would be 0 degrees. So here you can see on this sinusoidal waveform, I don't have any phase lag in between input and output signals. So these type of materials are basically known as ideally elastic solids. Now let us come to what are the effective ways in which we can actually characterize a viscoelastic material. Of course, there are n number of experiments and lot of tests to be performed on a material, but I would be emphasizing only on three, which are the most important means tests or characterization techniques for any particular viscoelastic material. So the first one is a yield point measurement. This can be done in rotational and oscillatory measurement, but when we talk about only yield point by rotational measurement, we have a completely different form of tests. Then we will discuss about the amplitude sweep, or you can also say it as a strain sweep. Some people also call it a shear strain sweep. And this is basically performed in a oscillatory mode. And then we will discuss about the frequency sweep, which is also performed in a oscillatory mode. And there are many more experiments which are to be explored, but because of limitation of time, we can of course cannot go through each and every experiment. Now let us come to yield point. Yield point, as I have mentioned, it is basically the limiting value of shear stress, and it is the minimum amount of stress at which your sample starts flowing when you are dealing with liquid samples, and when you are dealing with solid samples, it is the minimum amount of stress at which your solid sample is plastically deformed. So in this type of tests, using a using a rotational method, we mainly work on stress controlled mode. So here you can see in the graph, my x-axis is the yield stress, is the shear stress, and my y-axis is the deformation. So here in this type of experiments, we are controlling the stress and measuring the deformation. Now here, these type of curves can be divided mainly into three regions. In region 1, when we apply a very small shear stress, you would see somewhat an elastic deformation. So you would see a linear curve, means linear curve with very less slope. So you can see in region 1, when we started applying the shear stress, the deformation increases linearly, but up to some extent. After that, there is an abrupt change in the abrupt change in the deformation. So you can see in region 2, there is an inflection point, or you can see there is a sudden change in the linearity of this elastic deformation. Now, this particular region can be called as an yield zone, and the stress at which this limiting, or you can say this sudden change of the deformation happens, is known as yield stress. After this, on zone 3, you can say that my material or the fluid had started flowing, means like it is behaving more as a viscous material. So this is one of the way in which a lot of people are still measuring the yield stress from, where in shear stress control, in stress control mode, and with measuring the deformation with varying stress. In demonstration, I will show you one experiment with this type of information, and we'll see that there is first an elastic deformation, and after certain stress, there is an abrupt change in that deformation. Just to give you an example, this is an example of crude oil sample at various temperatures. So you can see over here in first zone, that is up to say 10 pascal of stress. You would have a linear curve up, and after approximately 10 pascals, there is a sudden change in the deformation. Now, this particular point, that is approximately at around 10 pascals, is the yield stress of this particular crude oil at 10 degrees Celsius. Now, if you decrease the temperature up to 0 degrees Celsius, you would see that your yield stress is increasing. So for 0 degrees Celsius, this elastic region is extended, and then after certain point around at 50 pascal, there is a sudden change in the deformation, showing that 50 pascal is the yield stress for this particular crude oil at 0 degrees Celsius. Another test that we usually perform is an amplitude sweep. This is done in oscillatory mode, and the basic preset in these type of tests is that we keep on changing the amplitude. That is, we keep on we are controlling the strain or the deformation in the material, keeping the frequency fixed. So if you consider a two-plate model, your top plate is moving to and fro up to certain displacement. Here you are changing the displacement, keeping the speed of the oscillations constant. So you are keeping the frequency constant and changing the amplitude, that is the deformation. So here you can see the results. What we get is somewhat like this over here on the left hand side, where you can see in these some type of material, especially when in case if you are dealing with solid materials, initially you would find G prime dominant over G double prime. That would suggest that at lower deformations, the sample is acting more like solid, and as you increase the deformation, after a certain point, you would see that this G prime curve is moving towards G double prime, and after a certain point, there will be a crossover. Now, when you consider the point of or the deformation at which this G prime curve starts deviating towards G double prime, is called as linear viscoelastic range. So if you consider a stress or stress and deformation curve, you can see this elastic deformation, that is the deformation up till which the internal structure of your material is constant. You would find same information in an amplitude sweep, that is in terms of linear viscoelastic range. That would mean that below this deformation, the elastic structure of your material or the structure of material is intact. After this deformation, there is some sort of plastic deformation in the structure. So you will get the linear viscoelastic range, and this linear viscoelastic range is really very crucial when in order to get an information about the physical stability, or in case if you are working with the polymer melts, it is really very important to characterize this linear viscoelastic range, because this particular range or deformation is to be used in case if you are doing any temperature dependent tests or time dependent tests or any other thing. So ideally you would have also get a flow point, that is after this crossover point you can see that now my G double prime is dominant over G prime. That would mean that after this point my material, even if it was solid at the time when we have not deformed it, after this particular deformation, my material or the material what you are testing had started to flow. So this is also very much crucial for various applications, of course. For example, in cosmetic applications where you need to shear your sample or shear your means product and then use it, this particular flow point is very crucial too. Another type of curves that we can get from amplitude sweep is something like that. On the bottom left image, you can see here, instead of getting G prime dominant over G double prime, we are getting G double prime dominant over G prime. So here you can see that my material or the material what you are testing is already behaving as a liquid or liquid material. So you can see over here G prime that corresponds to the viscous part is always dominant over G prime that corresponds to the elastic part. Although in some cases we need to do oscillatory tests or frequency sweep for these type of samples too. So that's why the linear viscoelastic range is also crucial in this type of material. Although in this type of material, elasticity is present, but viscous part is dominant. So we can always consider the plateau of G prime curve in these type of samples as an LVE range. But yeah, this is the major difference between the solid-like material and the liquid-like material when we are testing it through amplitude sweep. So this amplitude sweep can actually give you various parameters which might be interesting for you. And in case if you are going through a lot of publications, you would often found these parameters mentioned in the result. So it can give you the gel strength. And when you talk about gel strength, it is the stiffness of the sample. And it is given by the plateau of this G prime curve. So we call it a gel strength, or you can, in simple terms, you can understand this as an strength of the material. So this is also very crucial information, which definitely a lot of application requires. Then you can determine the linear viscoelastic range. That means the elastic range of this of a material. That means the deformation up till which the internal structure of material is not changed. Then you can also determine the yield stress using this. So here, after this LVE range, you would find the yield stress somewhere over here. So yield stress in this case would again be the stress value after which the plastic deformation of that material started. And also you will get the flow point of the curve. That means the point after which your material starts flowing. This is a typical example of a drilling fluid. Here you can see various comparison between three drilling fluids. and you can see that blue one has the maximum yield stress, and also you can see uh, the flow point of the blue curve, that is the third type of drilling fluid, is at the highest. So higher the flow point, better is the stability. And when I talk about stability, here I am talking about the storage stability. So when you talk about green one, you have intermediate flow point, and of course the yield point is lesser than that of uh, the blue one, and red one has the least yield stress or yield point. And also you can see over here the flow point of this particular sample, the red one, is very less than compared to other. So when using something in for actual applications, the blue type of drilling fluid would be most appropriate. Another test that we can perform is the frequency sweep. Now, if you remember in amplitude sweep, we discussed that uh, we are varying the strain, that is, we are varying the deformation, and we are keeping the frequency, that is the speed of that oscillation, fixed. In frequency sweep, we do other way around. So we keep the strain fixed, that is, we fix the deformation, and we vary the speed, or we vary the frequency. So here you can see in this particular plot, if it is represented in a sinusoidal manner, you can see over here we are ranging from very high frequency to very low frequency. Now, another thing which is important for in frequency sweep is that, as you know, that frequency is inversely proportional to time. So most of the time, frequency sweep is somewhat like a time dependent test. Means you can actually see the property of that particular material with varying time. So where your high frequency region, that is over here, represents a shorter time regimes, and low frequency regions represents a higher time regime. Now the preset of these type of tests are that the strain what we keep fixed, or we means like we put it as a constant parameter, is basically taken or chosen below LVE range. Why below LVE range? Because we need to make sure that while doing the frequency sweep, the internal structure of that material do not change. In case if it is changing, then most of the results that you are getting using a frequency sweep, or the parameters that you are determining, would not be correct. So it is very important to keep the strain constant, or constant and within the LVE range. So for example, if we get an LVE range of 10% for any particular material, frequency sweep we always need to do below 10%. So this is something which is very crucial. And same way, in case if you are doing any temperature dependent study or time dependent study, it is important to keep the strain within the LVE range, that is within the elastic limit. This is a typical example of how frequency sweep of polymer looks like. Now, most of the times when you talk about different samples, say, for example, if I have some food product, or if I have some cosmetic product or pharmaceutical product, ointments, the frequency sweep curves may be different. I'll show you some example. But for uncross-linked polymers or polymer melts, this is the typical type of frequency sweep curve that we get, where initially at higher frequencies, we get G prime dominant over G double prime. But as you go towards a lower frequency regime, that is longer time regimes, you would see that this G prime is actually deflecting towards G double prime. And at a certain point, there is a crossover, after which your G prime is dominant over G double prime. Now, this particular crossover point is very, very crucial for any polymer scientist, or you can say any polymer production plant or industry. Because this particular point would give you an information of a relaxation time. Now, relaxation time, if you remember the example of dye swelling, where there was when the material or when viscoelastic material comes out of the dye, it stretches or it tries to regain its structure. And the reason for that was mainly we have given an improper relaxation time, or our dye length is not big enough. This type of information is very crucial in designing the dye length and in determining how much time at least that melt has to be in the extruder in order to avoid these type of defects. So this type of relaxation point is basically related to complete relaxation of the molecular chains that are entangled. So we need to give this much of time in order to extrude any particular product, polymer product. Also, it will give you the information of molecular mass. So this molecular mass, in case if you can say that if this crossover move towards left, you can say that the molecular mass is very high, and in case if it moves towards right hand side, you can say that molecular mass is lower. Also, in case if it moves up or down, that will also give you an idea about the molecular mass distribution. Now, this is a very good way, I would say, to determine the molecular mass distribution. And in fact, most of the times, in case if you are interested in molecular mass distribution measurement, most of the times you can use these type of tests and compare it with GPC. So rheometers usually are very sensitive at a lower frequency regions. So the data what you are getting over here can actually complement the results what you get from GPC instruments. So this is a very effective way to accurately determine the distribution, molecular mass distribution in your material. So the advantages of frequency sweep is, of course, it can give you the molecular mass, and it can also give you a molecular mass distribution. It can also tell you about physical stability. So physical stability, especially when you are, for example, you are storing your product for a long time, like paints and coatings, then it is really very important to know or have some idea about the physical stability of that particular. Now, frequency sweep, being a time-dependent study, can give you an idea about the physical stability of that. Or in case if you are doing some sort of reverse engineering practices, say for example, if you are following some standards or some reference materials, then you can always compare your product with those reference material and determine whether your product has a similar physical stability as that of reference product or not. Then it can also give you idea about shelf life. It cannot quantify shelf life, but yeah, means like it can actually give you an idea about the shelf life of the material, and also it will tell you about the phase separation. So it will tell you whether there is some sort of phase separation which had happened in your material or in your sample, or it is going to happen in near future. So you can actually predict that phase separation phenomena also using a frequency sweep. This is a typical example of uncross-linked and cross-linked polymer. You can see over here, red curve is cross-linked polymer, and the blue curve is uncross-linked polymer. Here you can see in uncross-linked polymer, initially at higher frequencies, you would see that G prime is dominant over G double prime. And as you go to lower frequency regimes, that means longer time regimes, the G prime, there is a crossover, and after which G double prime is dominant over G prime. So here you can say that this crossover point is a relaxation point of this polyethylene sample, and you can say that this much amount of time has to be given to this polyethylene in case if you are using it for extruding or you are developing any particular polyethylene product. So this relaxation time information is really very crucial for polymer processing and polymer manufacturing. Another thing, for uncross-linked frequency sweep, uncross-linked polymer frequency sweep, you can see that there is no crossover. So you can see over here, red curve, the square G prime represented in red squares is always dominant over G double prime, which actually shows that the uncross-linked polymer is already in a solid form, and with respect to time, it is becoming more stiffer. So here you can see the magnitude of, at low frequency regime, the magnitude of G prime and G double prime is has increased. The difference between the magnitude compared to at a high frequency, that this particular type of data would mean that your material or your sample is getting much more stiffer. So if the magnitude of there is a very high difference between the magnitude of G prime and G double prime, then you can say that your material is much more stiffer than compared to what it used to be. So most of the curing experiments, when you talk about curing experiments, they usually deal with such type of information or such type of data where you are actually seeing your G prime having a very high magnitude compared to your G double prime. Then there are other type of frequency sweeps also for ointments, for paste-like samples, which I would show you some examples of in the demonstration, and we will understand how to characterize or how to know, say, the physical stability or how to compare the physical stability of any particular product. Then there can be some temperature-dependent studies using the oscillatory tests. Here you can see an example of a crude oil, wax precipitation in crude oil. Here in this example, we have actually fixed a microscope with our rheometer. So we have an accessory called as rheo microscope, where we attach a microscope to our rheometer, and we can simultaneously take various videos and images with the measurement. And that complete means you don't need to manually take images or videos. The software can do it for you. So here you can see various stages of this crude oil precipitation with temperature, and you can compare it with the oscillatory tests. So here you can see initially at a higher temperatures, your G prime is dominant. That means it is somewhat behaving as a viscoelastic solid, but you can also see that the magnitude of G double prime is not that much, it's not, the difference is not very high. So it is somewhat in the means like viscoelastic solid range, but still you have a lot of viscous part or viscous property in that particular sample. As you decrease the temperature at a certain point, that is 30.98 degrees Celsius, you can see some sort of precipitation, wax precipitation has started. And if you further lower the temperature, you can see this wax precipitation actually increases and your wax starts to crystallize. And at a lower temperature of say 25 degrees Celsius, you can say that it has turned to more like a viscoelastic, a viscoelastic solid. Initially, it was viscoelastic liquid. You can see over here. This actually, sorry, this square bracket, this dominant one behaves as a G double prime, and the lower one is G prime. So you can see over here at higher temperatures, your G prime is dominant, G double prime is dominant over G prime, and as you decrease the temperature at a certain point, after this, your crude oil solidifies. So you can say, you can accurately correlate this point with the microstructure of the crude oil. So here you can see at around, say, at around 20, at around the crossover is at around, say, 20, 30, 33 or something like that. We don't have an image in 33, but we can of course always correlate using our Rio Compass software. But you can see over here at 25, if I go to 25, the crude oil completely behaves as an solid material or viscoelastic solid. Now, this whole experiment is basically done under LVE range. So it is really very important to define the linear viscoelastic limit of any particular material before testing it, before doing a temperature dependent study or time dependent study. Another example is polymer modified bitumen. And here you can see definitely bitumen is a material which is very sensitive to temperature, and even a fraction of change in temperature may change some sort of viscoelastic property in the bitumen. So it is really, whenever you are testing a bitumen sample, it is really very important to make sure that the temperature what you have chosen is accurately means you can say that your sample is also at that particular temperature. So you need to make sure that there is a minimal thermal gradient as well as very good thermal homogeneity in your sample. So that's why in order to test most of the bitumen sample, the waiting period before the measurement is always 10 minutes as per ASTM and R. So this is something which is very crucial. And here you can see from data from minus 20 to 100 degrees Celsius, where you can see that your G prime at lower temperatures, your G prime is dominant over G double prime. That means your bitumen sample acts as a solid material. As you increase the temperature, at a certain point of around, say, around 20 or so, there is a crossover, and after which you can say that your G double prime starts to dominate over G prime. At 100 degrees Celsius, you can say that the magnitude of G double prime and G prime are increasing. That means it is becoming more and more liquid-like. Because at a very high temperature, bitumen sample also acts as a Newtonian fluid. So as you increase the temperature, you will see that this the magnitude of G double prime is pretty much higher than that of G prime. With that, I would like to end this particular part of session. Hope you got something out of it, means like how these oscillatory tests are performed and why it is important to test viscoelastic materials, especially in oscillatory mode. So as I have explained, viscosity only gives you information about the flow behavior, but viscoelastic studies give you information about the flow behavior as well as the structural part. Without characterizing the structural part, you cannot know about your particular material. So this is something which is very important, and nowadays most of the rheological measurement, whatever you would see in literature or in quality analysis or quality control labs, are related to oscillatory tests. So in case if you have any questions, I can answer those, or you can also ask in case. I'll just stop sharing and I'll move on to our next speaker, Dr. Fatia, and she would be presenting her work related to rheology. She had quite a decent experience in rheological measurements, so I hope you would learn a lot from her talk. Thank you very much, and I'll just switch over to Dr. Fatia.
Yes, hello.
Hello, yes. Yeah, we can hear you. Now you have a sharing right.
Yes.
So you can actually share your screen and go ahead with the presentation. Hello?
Yes.
Yeah.
To share my file. Already share.
Yeah, there is a share.
Yeah, but still the icon is inactive, so I couldn't.
Okay, so let me 1 second. I'll just give you some more. I have already made. Just check now.
Oh yes, yes.
Yeah, thank you. Yeah, sorry.
So it's clear now. Can you see my presentation?
We can see your screen, but can you please raise your voice so that because I think your voice is very
Okay.
means like it's the volume level is very.
It's okay now.
Yes, it is okay. Yeah.
Assalamu alaikum wa rahmatullahi wa barakatuh. So this is Dr. Fathia, lab supervisor, rheology lab supervisor in Petroleum Institute. I'd like to welcome all our line guests. So during this session, some experimental results will be presented for a study that was carried out in the rheology lab to emphasize the importance of rheology and valuability of equipment and devices in complementing the rheology studies. So the project that I'm going to present title experimental results on rheology of waxy crude oil. So before I'd like to give you a bit background about waxy crude oil. What is the waxy crude oil? Waxy crude oil is characterized by a high content of paraffin and a mixture of heavy hydrocarbons, alkanes, which usually range from C18 to up to C14. Also, it's about a third of the oil produced worldwide has high wax content. It's about from 15 to about above to 40%. So here, this table shown some Libyan waxy crude oil. If you can see here, the wax content around from 8 to above 29. The second question here in this session, why is waxy crude oil is important? Because the first thing is have low sulfur content, which makes them more desirable from an environmental viewpoint. Also high ABI gravity, and also the good white product yield using this such crude oil. Also, it's already feedstock for wax manufacture.
Hello, sorry to interfere, but can you just raise your voice a little bit so that because some of the participants are not able to hear, means like your voice is very
okay.
low.
Okay.
Yeah, please. Yeah.
Okay,
Or you can just take the headphone near to your mouth, maybe. That's why.
Okay.
Yeah.
I tried to go to do. Can you hear me now?
Yeah, it is
Here.
better. Yeah,
What
now
about my
better.
voice now? Better?
Now it is better. Yeah, it is
Okay.
better. Yeah.
Sorry.
Yeah. Thank you.
Okay. So,
Yeah.
okay.
Sorry.
I
Yeah.
will say. That's okay. That's okay. No problem. So I will repeat this slide. As I told before, waxy crude oil is important for this low sulfur content and also high ABI, and it's very good white product and feedstock for wax manufacture. So here, another question, what is wrong with waxy crude oil? Why such crudes makes problems in pipelines and so on? So the main problem here with waxy crude oil is the risk temperature drop near or below the pour point, which makes restarting flow in pipelines very expensive. So as Dr. Muhammad said yesterday, when the ground temperature is appreciably below pour point, the wax crystal separates out and the crude turns from liquid to suspension. With further temperature reduction, crystals growing, agglomerating, and the crude oil's loss of flowability and becomes non-Newtonian flow behavior. So that's why the wax will precipitate and makes problem. So we have to maintain the crude oil hot throughout long journey. Unfortunately, power cuts occur leading to loss of heating, and also wax precipitation puts pipelines in danger of blockage, millions risk. So to avoid this, waxy crude oil also creates problems in production, oil production, for three reasons. Restricted flow due to reduced inner diameter of pipeline, and also increased viscosity. It means leading to pressure losses and settling of wax in storage tank. So this slide shows mitigating of wax problems. There are many methods to avoid or to mitigate these problems. First, to prevent or reduce the occurrences of the deposition by keeping the flow temperature well above wax appearance temperature and also keeping flow rate up certain limit to ensure mixing during the flow. Second type is mechanically remove and treat the deposition after it's already occurred. So, however, in order to select most economical and technically suitable method, waxy crude properties have to be accurately characterized. So here are some examples for mitigation of waxy problem. Mechanical, here use bigging, inserting some metals inside the pipeline, and this method is a bit expensive, using to clean the pipeline. And thermal method, there's two ways. First, initially subject the crude to a special heating cooling treatment cycle to melt wax crystal and reduce also pour point and pumping viscosity. The second method, heating both crude oil and pipeline, and of course this type of treatment use it to just for short pipelines by using electrical steam tracing or the use of cut line. The third type of mitigation the wax problem is adding wax inhibitors. So here I give here's the two main wax inhibitors types. First, it's called wax crystal detergent or suspensions, or dispersants, and the second one, wax crystal modifier. So wax crystal detergent, it's surface active agents that hinders the wax crystals that form from assembling into gel network. There is some example, alkyl sulfonates and fatty amine. The second one is crystal modifiers, which is polymers dissolved in solvent. And this the job of this wax crystal, they insert themselves between, thus. So these work like a pour point depressant. I mean, focus in only reduce the pour point and sometimes viscosity. Because, okay, the most widely used being vinyl acetate, ethylene vinyl acetate. So in this research that I'm going to continue, we focus only on consider the wax inhibitor. We choose wax crystal detergent, one of them, and wax crystal modifiers. So here the question is how to operate pipeline against this eventuality. The answer, reduce the potential for precipitating through two things. Blending the wax oil with light oil, low wax content, and using chemical wax inhibitors. So this is what this lecture is about. So the question to be answered is what the minimum restart pressure to use and at which rate the pressure should be increased to this minimum pressure to restart the pipe as quickly as possible. This slide shows the approach to studying this problem. We have here a case study based on ABU waxy crude oil has about 29% wax content, and the wax inhibitors before we choose this sort of wax inhibitors, we do a comprehensive, comprehensive survey to choose available chemicals. So we choose light oil has about 6.4 low wax content and have ABI gravity about 36, and also the pour point minus 9 Celsius. So we select also wax crystal detergent, wax improver called the ROA, and wax crystal modifiers called PBD. So here the specification and concentration that we use in this research. Certica crude oil, we talk or we used, we applied 20% volume. This is the best, volume we choose. And the wax inhibitor, we used 500 and 1000 ppm. For PBD, we choose or we used 1000 and 2000 ppm. So here, the scenario of the work, we divided the scenario divided by three consideration stages. The first one, when normal situation, means pipeline full production, oil is flowing hot and no problem, and high shear dynamic rheology we use. The second consideration is immediately after heating is cut off, so nearly zero shear dynamic rheology. The last one, which is the worst, when the flow ceases completely. There is no more flow in waxy crude oil. So, but oil still continue to cool. So the question here, how much pressure do we require to restart flow? Here we are going to talk about yield stress static rheology. So the question here, what will be the effect of dilution with another oil or chemical inhibitors in normal situation? The second consideration, what will be affect the same thing, dilution with after heating is cut off. And the third one is what will be the effect of dilution with another or the chemical inhibitors, the situation flowing the above when the flow ceases completely and the oil continue to cool. So these form the three work package of the research complemented by, first, we have to characterize the oil and the additive used, and then also microscopic observation, it's see the gel formed to understand how these develop upon cooling. So before starting the rheology lab, the crude is characterized first. So here we use DSC, differential scanning calorimetry. I couldn't use laser or the mouse. Show I'm talking about would help me. Ahmed.
Hello, can you check?
Do you see the mouse when I move it
No.
along the slide? So how you can
No, you can just right click and just opt for a pointer on the screen. Yeah, right click and see whether there is an option for pointer. Or you can use the thumbnails on the extreme left. You would see some lines and all those things. You can actually use them in order to explain.
Yeah, can you see this?
Yeah.
Okay.
Uh,
Can you see now the?
No, we cannot see right now. But you can always use the thumbnails over there, so you can see the line and all those things over on the left hand side along with the screen. So you can use the paint and all those things for in order to explain. Pen tool or something like this.
So before starting the rheology, as I've said before, some equipment here used the differential scan calorimetry and GC high gas chromatography and cross-polar microscopy. Dr. Muhammad yesterday had gave a bit of information about these equipments. So here, differential scaling calorimetry is used to measure enthalpy changes due to changes in the physical and chemical properties of the crude as function of temperature and time. This diagram show the heat flow curves during the measurement. So the first peak considered or it appeared the first crystals formed through the while cooling. This table show chemical additives had different effect on what, as you see here, the Abu Tafel untreated 68 and decrease adding 2000 BBD, 1000 ROA as well. So here ROA had best performance followed by BBD. Effect of chemicals on pour point. So pour point is the lowest temperature below which the crude ceases to flow. It means stop to flow. So it's a crude assessment to flow out a heated jar of the oil tilted horizontally from its initial vertical position. So we use other methods here. In the early years of the oil discovery, pour point was a property used to differentiate between various oils. Clearly, it's an indicator of wax gel formation, but not as sophisticated as the heat flow curve determined from VSC calorimetry, which gives a precise measurement of wax appearance temperature. Also, modern rheology as well can determine the gel point at controlled cooling rate, as it will be discussed later. So here the first, through the cooling, the first wax appearance temperature first crystal, and then when the crystal is become more, we have here gel point and pour point, the last stage of the. Here some results of the pour point. No significant effect can be noted. However, this is not the end of the story, as will be shown and discussed in the rheology result part. So here we couldn't, consider only pour point to select some chemicals, because even there is no change in pour point, we will find the viscosity improve, and I will show you later in the rheology part. Here, the effect of chemicals in wax composition by using gas chromatography. Waxy crude oil contains paraffin, as I said before. Were useful in establishing the effect of addition of chemicals on altering carbon chain length of oil. So through these two figures, which treated with the low wax oil and treated with some chemicals here, ROA, high temperature gas chromatography is a very good tool in characterizing carbon number distribution of wax crude oil. So in case of dilution, observe up on dilution with light low wax crude, the long chain are broken and distributed among lower carbon number molecules. Hence, the distribution was shifted to the left side. Cross-polar microscopy provide valuable information and image of the structure, morphology of wax crystal formed upon cooling, observing the effect of temperature and cooling rates on the size and size distribution of formed crystals. So this image show the effect of cooling rate on average crystal size and density for ABU at 30 Celsius. So decreasing cooling, it means extending the cooling time, which give more time for crystal to grow in size. Also here, by using cross-polarized microscopy, we see here the beneficial effect of wax inhibitor addition ROA in altering wax gel structure, reducing network competence. So here in the right side, it's we can see the crystal becomes large and there is a gap, void here. So rheology of crude and blends, we used two techniques, controlled continuous stress. It's a shear stress ramp test, and we use control oscillatory stress amplitude sweep at fixed frequency test. The parameter we investigate here, it's we consider effect of heat, effect of chemical type and dose, and also effect of cooling rate, and the last one, effect of stress loading rate, the rate of shear stress applied, Pascal force per minute, Pascal per minute. So the scenarios of work, first one, as I said before, normal situation, we choose a shear rate range about, we choose two shear rates, 10 and 50 reciprocal second. The temperature range from 80 go down to 30 Celsius, and cooling rate 1 and 0.5. The chemicals studied slow wax crude and ROA and BBD chemicals. Also here, the second consideration is immediately after heating is cut off. So here the shear rate, just 1 reciprocal second, compare with 10 and 50, because here we talk about near zero shear dynamic rheology, and temperature range from 80 to 30 as well, and the same chemical studied. The last scenario or the last consideration is when the flow ceases completely, the oil continues to cool, and temperature here we choose from 80 to 30 and 35, 40, 40. The same. So rheology part, first we use the CVO 100. Have very good resolution, shear rate range down to 10 to the power minus 5, which is very good to trace any change in shear stress. So rheometer is used to measure the apparent viscosity at full production. Here shear rate 10 and 50, and near shutdown shear rate is 1, and totally shut down, yielding after the oil was statically cooled. So the mean also, yeah, I mean, we use it or we measure the apparent viscosity, and we measure yield stress and gel point temperature. So now let us move to samples of some results. So the first consideration here, pipeline full production when it's normal situation. So it's just a reminder that in this research, we considered three scenarios. The first, this is the first one, the capacity of full production, but under cooling rates, which mimic the real condition. So we studied the two cooling rates. This methodology will enable us to find the temperature at which the crude will departure from Newtonian behavior towards non-Newtonian. So here, dilution with light crude is economically cheaper compared with chemicals, which might have adverse effect on quality. So here we can say, or we can observe the beneficial effect of wax inhibitor reduction of apparent viscosity. Hence, when we say reducing the apparent viscosity, it means bumping pressure. Here we say again dilution with the, you can see here use ROA 500. You can see the reduction in apparent viscosity. Here the reduction about 50%. Here the reduction about 64. So we can say here again dilution with the Certica more beneficial compared with the ROA. The second consideration was immediately after heating is cut off. Here the shear rate is 1 reciprocal second, and also we can see the beneficial effect in reducing the apparent viscosity. The figure, this figure zooming in the right side, can see from 180 Pascal second, the viscosity reduction to 74. So the percent about 60 reduction. So adjusting much saving to be made, heating and or overcoming the problem for this the crude oil drilling just before shutdown. This case is different from the previous two cases since the cooling here quiescent. It means without flow. So the yielding of waxy crude oil undergoes several stages as shown in this figure. So these two graphs represent the difference between old and new advanced rheometer. In the right side, the only shear rate we could trace or monitor is only 0.01. However, in the left side, we could use, by using rheometer, advanced rheometer, we goes up to 10 to the minus 5. So it's very good. The advances in technology enable us to closely trace the three regions in the yielding process. First, elastic creep and fracture region, finally reaching the viscous region at which flow commences. So elastic region where the gel is solid and applied stress was not enough to break it. By increasing the stress, the gel starts to creep or stretch as the stress continue. As the stress continue to increase, the creeped gel can no longer resist the stress, so it began to fracture at tau S static distress means. With further increase in stress, tau F means the flow static flow. flow static, it become complete fractured and starts to flow as the viscous region. This is a figure ABU crude at 30 Celsius, which is the worsening in temperature here. So both elastic limit and the static yield stress are dependent on the strength of the interlocking network of wax crystal, the oil, before the structure is disturbed. However, or while the yield stress is related to the concentration and size of the wax crystals in the crude oil after the structure is completely destroyed. Static yield stress is the most interested because the stress value when the fracture occurs, as this stress value effectively determines the pump capacity required to initiate flow and ensure pipeline restart. So we can use this equation to predict the restarting pressure. So here, this figure showing the benefit of treating ABU with chemicals and blending at low wax crude oil. It can be clearly here. So the chemicals were successful in lowering yield stress, means lowering pipeline pumping pressure required to restart the flow after shutdown. So here, the cooling rate, we use it, the 0.5 means more long cooling time, which represent the pipeline shutdown period. The minimum reduction here in this figure was obtained was about 70% with chemicals, which is very good. And here another figure, the 40 degrees centigrade, treated with the ROA and BBD. So here we can see the difference between the ABU untreated and its chemicals. Also here we can see dosing with 1000 ppm ROA at 30 Celsius. But here the stress loading rate was 100 Pascal per minute. So we can here see the difference clearly. Here the gel point as determined by oscillatory technique. So gel point test conducted by fixing small stress. Of course, small stress we choose when we did linear viscoelastic region before we go to this test, which will lead to measuring the changes of elastic module and viscous module, as Dr. Ornov explained in the first session, and give more valuable information about these properties. So the gel point can be found at the crossover of G prime and G double prime. G prime, of course, it's storage elastic module, and G double prime viscous module. Some examples, the effect of addition on the gelation point. So from this table, the cooling rate has a significant effect on untreated crude gel point. However, it's not the case for treated crude with chemicals. The chemical performed in lowering gel point performed well lowering gel point at cooling rate of 1 C per minute, and their effect vanishes as cooling time increase. So final remarks, during this session, some laboratory results were study that was carried out in the Rheology laboratory, Libyan Petroleum. The results show clearly the importance of characterization tools such as the gas chromatography, cross-polar microscopy in complementing any crude oil rheological study, and its role in solving flow problems caused by parachute, which in turn save the oil industry millions of dollars. Thank you for your attention. If you have any question, thank you.
Thank you very much, Dr. Fatia. And it was really very nice presentation on various aspects of rheological measurement in crude oil. I would ask all the participants, in case if they have any question, they can use a chat box, write their questions, and then we will answer them means after the demonstration session. Thank you. So let me switch over to the demonstration now. Second, I'll just start my camera. I'll just start my camera. Yeah, I hope you can all see. Second, stage. Yeah, so I hope you can all see the rheometer on your screen. So those who have not joined yesterday, again, I would just explain some details about this rheometer. So we have a motor head which will give the deformation and measure the torque, that is the stress. And when you divide the stress with the deformation, that is the strain, you get the shear modulus. Then we have an air bearing coupling. Now air bearing is basically used in order to enhance the torque measurement capability of any particular rheometer. And whenever means like in case if you are using any rheometer, please make sure that it is always an air bearing system, because air bearing is somewhat would guarantee your results would be much more accurate and reproducible. Then you have a temperature controller. We have a temperature controller hood. Now there are various temperature controller available with this particular system. This one is a Peltier temperature control, which can go from -40 to 200. And what we have over here is heating from the top and heating from the bottom. So in order to maintain a complete thermal homogeneity, what we have made is like we are heating the sample from the top as well as heating it from the bottom plate. This is the bottom plate where usually we keep our sample, and this is also Peltier temperature controlled. It can also go from -40 to 200 degrees Celsius. So today I would be measuring few samples in oscillatory mode. So if you remember yesterday, we have only done the normal flow curves, that is the viscosity curve, in a rotational mode where your geometry rotates on the sample, and we always measure the viscosity. Here we would be using, I have some paste samples. So this is a normal toothpaste, and we would try to measure this sample and measure its yield stress, as well as we will also see some sort of physical stability experiments for various type of paste sample in order to compare, say, the shelf life or the physical stability. So I'll just put a geometry. So today I would be using a PP25 geometry, because most of the paste samples, they do have a lot of filler particles, and those filler particles are pretty big in size. So it is always good to use a parallel plate geometry. And the lower dimension is to control the torque. So stiffer your sample is, better the torque is generated. So in order to like compensate with the torque, of course, you have a minimum and maximum limit of torque measurement. And in order to compensate that, stiffer the sample, uh, smaller is the geometry dimension. So this can be a thumb rule, means where you can decide which geometry is to be used for what type of sample. So here I am measuring a viscoelastic solid, and because I am measuring a viscoelastic solid, so even if I have a lower dimension geometry, the torque would be the sufficient torque would be generated at the motor system. So I'll just put this geometry onto the coupler, air bearing coupler. So you can see now the geometry is fixed. The geometry is fixed to the coupler. And also yesterday it was rotating on the sample. Today we will have it oscillate on the sample to determine the viscoelastic behavior of any sample. So I'll put some paste sample onto the bottom. You can see I have already placed my sample over here, and then I will lower down the geometry. So for that, I will share the software window. Yes. So I'll just share the software window. I hope you all can see the software window now. So I'll just go to the navigation panel, the control panel, and we'll lower down the geometry. So here we will be keeping a gap of 1 mm. So I'll just lower it down. So after it, now it is asking for the trimming. So I'll go and trim some extra samples. So you can see in trimming what we are usually doing. You can see all these extra samples which are coming out of the geometry. We need to remove that because when shearing, these samples would not encounter any of the stress or deformation, and probably can give, but still play an important role in the measurement or the values of stress. So that's why it is very important to remove these extra samples in order to get a much more accurate and reproducible results. So I'll just close this hood. So in order to maintain the thermal homogeneity. Now I'll continue. And I'll set the temperature. So right now the temperature is 21 and we have not set it. So I will just put say 25 only, and I will set the value. So now you will see the temperature will rise, and it will maintain up to 25 degrees. Now, the first test what I want to show you is the yield stress test. The same test Dr. Fatia also mentioned about different various regions of any particular paste-like samples or crude oil, where first region you would always have an elastic limit. The second region would be more like an yield zone, where your sample would plastically deform. And the third point is definitely when your system or when your material starts to flow. That means it behaves as a viscous material. So I'll just open this test. This is flow curve linear with controlled shear stress, because we are going to measure these samples in a controlled shear stress mode, where we need to control the shear stress and we are determining the shear strain. So here you can see from the measurement tab the parameters. So the parameters which we are going to use is from 1 to 100 pascals, and the density point is 2 point per pascal, which is okay, which is decent, and all the measurement parameters are over. Every point is at 1 second of time difference, because most of the times when you are doing any sort of yield stress experiment, the change in the behavior of the sample is always very sudden. So it is really very important in order to reduce the time difference between 2 points, so that you can actually analyze the behavior of your material accurately. Okay, so that's why we always keep 2 points at a very close distance or within very less time. And you can also see this analysis tab with this test template, where you would find the yield stress depending upon upward inflection. So if you remember the photograph, or if you remember that image of an yield point experiment, you can see that there is an sudden upward inflection, and that inflection can be your yield stress. And then you can also determine the flow stress using this. So we have already our sample loaded. The temperature is fixed at 25. We can just start this test. I'll type the name, and I will continue. It will automatically go to the diagrams. In case if you require, you can always add a waiting time in order to maintain or in order to reduce the thermal gradient. So this is shear stress versus shear rate. But in this type of tests, we are more interested on the deformation that is taking place by the shear stress. So you can see that initially this line was linear, and this particular up to say up to 10 Pascal, it is showing a linear behavior. After 10 Pascal also it is showing somewhat a linear behavior, but I suppose that, yeah. So you can see over here, it actually is showing you the yield point. This is the yield point. Here is what a little bit of that inflation had actually, or means had occurred, but there is no flow stress. So inflection is from at around say 54.5 Pascals, but after that we cannot see a flow stress region because still it is under the plastic deformation range. And when you talk about, say, in order to visualize this flow behavior, you can always increase the stress. So instead of 100, you can measure up to say 1,000 Pascal of stress and see whether you are able to get a flow point or not. So I'll also share you some example of my previous means tests on the flow curve. Yeah. So you see here, here also we have two paste samples with with different yield point, and here you can see the yield point for the first sample is at yield point of the first sample, that is this blue curve, is always more than that of the black curve. So usually when I talk about this black curve, this is basically close-up toothpaste. I actually measured it for some toothpaste manufacturing company. So this is a nice way to just show you how different toothpastes have different sort of yield stress. And when we talk about yield stress in toothpaste, it is really very important to know, because whenever you are means like taking out that toothpaste from a tube, you need to press that tube. So you need to press it until it flows out. So it is really very important to know the yield stress of any toothpaste. So here you can see the different yield stress of different toothpaste, where you can see this Dabur one is having an higher yield point than this close-up one. So that would mean that you need to apply more or much more stress to this blue toothpaste compared to this black one. So this is something which is like very important test, and is still a lot of quality control and quality analysis department in various manufacturing companies are using this type of test. Although I would say that these type of tests are of course good, means like they are well proven, but there is a slight bit of inaccuracy, or I would say means like randomness in them, because ideally in rotational test, what you are doing most of the time, you are rotating your geometry onto the sample. So you don't know, even if you are using a very low shear rates or very low stress, you don't know whether you are actually breaking or distorting the structure or not, because you don't know the elastic range. That is why oscillatory tests are better than compared to any rotational test, because it would actually tell you the elastic limit of your sample. It will tell you that this is the elastic limit, and above this particular deformation or this particular stress, the structure is present inside in that sample would be completely destroyed. So even with oscillatory tests, you can determine the yield point of the sample. So let us switch to the oscillatory test now. So here we have different sort of oscillatory tests. Of course, I am not going to means like show you all, but yeah, means like we can go ahead with the amplitude sweep. So this is a typical amplitude sweep test template where you can see measurement details. As I have mentioned, here you are varying the strain and keeping the angular frequency constant. So if you remember that animation where your top plate was moving and bottom plate was fixed, the speed at which that top plate was moving was given by angular frequency, and how much displacement is there on that top plate is given by your amplitude, that is the shear strain. So I'll quickly move this geometry above and change the sample, because in order to effectively measure any sample, you need to make sure that you use always a fresh sample. So I'll quickly change the sample and then we can go ahead with the measurement. Also in oscillatory test, you can means like do some sort of drying effect tests in case if your sample is prone to drying. So I'll just clean it, and now I will put a fresh sample. And lower down the geometry. So this is how it moves, you can see. So after getting up to a certain position, it slows down in order to, I would say, preserve the internal structure of that material. Now you can see that extra samples are coming out, and we will trim that extra sample and start off with our experiment. So I'll trim it. And then close the hood and then continue. Another key parameter that you need to always check is the sensor force. Sensor force is the normal force experienced by the motor system, and when you talk about it, it should be always close to zero, because this would mean that in case if it builds up high, this would mean that there is some sort of external force applied on your sample. And if you remember that the material properties do depend on ambient condition as well as any sort of external force, whether it is applied on the system. So this is something which is a very crucial point, that, and also in case if it builds up, you can give some sample some time to relax, and you can see now from 0.18 it is going down, because the sample itself is relaxing. So for any rheological measurement, it is very important to keep on checking this sensor force, because that would mean that whether there is some sort of external force applied on the on your sample or not. So I'll just go to start, and I'll just start the test. So it is definitely already, it is means in the flow chart of for the test, that to give some time here, you can change it to maybe 3 minutes in order to completely relax your sample. I'll just skip this part because in order to save some time. So here on the y-axis, you can see G prime and G double prime, and on x-axis, you can see the deformation strain in percentage. And if you see on the right hand side, you would see shear stress at x-axis and G prime and G double prime at y-axis. Although we are working in a controlled shear strain mode, but still you can get some plot of shear stress and G prime and G double. And all the data, whatever is there, you can see over here the details, the storage modulus, the loss factor, and the torque. Loss factor is also our damping factor. And yeah, means like in case if you want to see something else, say for example, I also want to see phase shift angle, then you can always add. So if I add phase shift angle, you would see that the phase shift angle is around 18 degrees. If you remember, if phase shift angle is lesser than 45 degrees, so 45 degrees, then we can say that the material acts as a solid. So here also you can see that it is 18 degrees. That means our paste is acting as a solid. And you can see now, if with increase in the strain percentage, you would see that there would be a crossover. G prime is moving towards G double prime, and at some point of time they will have a crossover. So if you consider the elastic range for this particular product, it would be somewhere near here, because after this point you can say that the deviation took place and your sample actually start deflecting towards G double prime. Now, of course, the yield stress from these type of data can be different to what we have done in our previous test, because as I have mentioned, in that test you don't know, even say you are applying 1 Pascal of stress onto your sample, you do not know that whether even at 1 Pascal there is some change in the microstructure of that sample. Although here in this case we can work from very low deformation and accurately see at which stress or strain value there is some sort of plastic deformation in our sample. So I would say this is pretty much better compared to any other yield stress test that we are doing. Although those tests are also very widely used, I would say, and still means like lot of researchers use controlled shear stress or controlled shear rate tests in order to get a yield point. But this is also something which is useful to get a yield point of any particular sample. So you can see now it is going to have a crossover, and you will get a flow point. Means the minimum stress over here at which the sample starts flowing. So you can see it was about 100 Pascal. So that's why we were not able to get any viscous behavior or flow behavior in that template in our previous test. Sorry. So the flow point is around, say, I would say it 120 or something, maybe. Yeah. So here it will automatically generate the report and end the test. So let us go to the diagram again. Here you can see, so my LVE range in this case is 0.03. Now, the permissible range, what I should use for my next frequency sweep is 0.03. Although, sorry, it is 0.01, but my LVE is 0.03, and after that, there is a plastic deformation in the sample. Now, you can also see a flow point over here. Now, flow point is saying that it is 77.8 Pascal is the flow point. Means after this much of stress, your material would start flowing. So yield stress also we can determine it through here. So we can select the data, and we can look at this. We can select this yield stress calculation on G prime in a logarithmic curve. So I'll select this, and I'll. Yeah. So you can say that here it is showing like yield point of 71.88 Pascal, which is, I would say, closer to the previous one what we have measured, but it will also give you the point at which you can say that there is a complete destruction of the internal structure. So here you can see the yield point. You can determine the LVE range, and you can determine the flow point. Also, there is something called as gel strength. So gel strength is basically the magnitude of G prime. So this you can report it as a strength of your material at a very, very low deformation. And you can also see the plateau. So even in case if you are extrapolating it to the lower strain range, you won't find much of a difference. So you can say that this is the strength of my material. This is how, means, or you can say the stiffness of my material. So this is an amplitude sweep. Now, in order to do any time-dependent study in frequency sweep, we need to use this LVE range and measure it. So we'll go to now frequency sweep quickly. Yeah, so here you would see just opposite of amplitude sweep. You can see in parameter, my shear strain is fixed, which I would always put it in like what within my LVE region, and I am varying my angular frequency from 100 radian per second to 1 radian per second, 0.1. So here I will just to save some time because this is a time-taking experiment. So I will just put it 1 radian per second so that at least means like it will be finished early. So although you need to change the sample for every run, but just to save time, I'll just start on with the same sample what I have tested earlier. Although you need to change the sample every time. So here you can see that this space-like sample is having G prime always dominant over G double prime. That would mean that this is acting more like a solid, and the slope of this G prime would actually give you a physical stability of your material. So if you have anything means like means if you need to measure means if you need to compare the physical stability of your sample, you can actually measure the slope of different sample, which I will show you in a pharma example, and you can actually measure it. So you can see at low frequency regimes, the data points are the rheometer is measuring much more slowly, means like you can say it is spending much more time. So the low frequency regimes are always longer time durations, and high frequency is always shorter time durations. And the slope would actually give you the physical stability or comparison in the shelf life. So if you have seen the polymer one, it was completely different where you need to see the crossover point, that is crossover in between G prime and G double prime. Although in this case, you can see there is no crossover. And if there is a crossover, that would suggest you some sort of phase separation. So which is not desirable. For any consumer products, what we use day-to-day life, the crossover itself is not favorable for usage, because crossover would mean the phase separation or physical instability. So ideally, this line should be perfectly flat, but no material can actually provide give you that sort of data, but it still means like this should be, even if you extrapolate it to the longer time regimes, that is to the lower frequency, it should not tend to crossover. So that would actually suggest that the shelf life or the physical stability of your material is better. To show you some examples, I'll just let me check this one. Yeah, so you can see over here different, these are food samples of different mayonnaise. So there is a full fat mayonnaise and low fat mayonnaise with some cream. This I have measured for some food industry. And you can see comparison between the frequency sweeps at a lower frequency regime. And you can see that I have also measured the slope. So if you consider, say, this cream type of sample, so lower the slope, better is the physical stability. So if you look at this thick cream slope, that is 0.04, this is the most physically stable cream sample within from the other ones. Same way, if you want to check that of mayonnaise, whether for full fat and low fat mayonnaise, and you can see that both these mayonnaise are equally say stable, means like there is no difference in the physical stability of these mayonnaise sample. But when you look at the cream sample, of course, means like this blue curve, or you can say the pink one, thick cream, is much more physically stable. And you can also say that shelf life of this particular cream is higher than compared to other creams. So this is how we can actually determine, get an idea about the phase separation, shelf life, as well as the physical stability. Another example, what I want to show you is for polymers, and how effective it is for polymers, these type of tests. So this is a template for polymer. For polymers, we have tested a polymer sample using a frequency sweep with at 190 degrees Celsius, that is polymer melt, and with the strain of 5% and frequency from 100 to 0.1. And this is the result what we have got as a crossover point. This is the relaxation time. Initially, G prime was dominant over G double prime, and after the crossover, G double prime is dominant over G prime. And this crossover point actually suggests the relaxation time and time for a polymer melt or polymer molecules to get relaxed or get completely independent of each other. Also, you can see the loss factor in this, that is G double prime divided by G prime. So because it is more, it is showing the loss factor always show the behavior of viscous behavior of material. So you can see that with decrease in the frequency, the loss factor 10 delta is increasing. Also, the important parameter we can get it from here is a complex viscosity. Now, for paste samples, for polymer samples, this viscosity will give you much more better information compared to the shear rate viscosity or steady shear viscosity, because here you know that your sample is there is no wall slippage and at a higher shear rates, and you will get approximately similar sort of viscosity. In fact, there is one mathematical formulation known as Cox-Merz rule, which actually describes the relationship between the complex viscosity and the dynamic or shear rate viscosity. So ideally for polymers, according to Cox-Merz rule, the complex viscosity is always equal to steady shear viscosity, what you are measuring in a rotational mode. Another advantage of this is you can actually get a very nice molecular mass distribution. So here you can see the molecular mass distribution. This data actually can be converted into relaxation spectrum, like over here. So this is a relaxation spectrum, and this relaxation spectrum can be converted into the molecular mass distribution. Now, in order to get a complete molecular mass distribution, at least you need to define few parameters what you are expecting. So, because, for example, in case if you are working with the polymer blends, those blends can be bimodal or they can be monomodal. So you need to define all these variables in order to get the molecular mass distribution. So for example, if I select over here, here you need to select the material properties, of course. We also have a complete library of material properties which you can input, and then you can define what you are expecting. You are expecting bimodal or you are expecting unimodal. There is also a function called auto, where software automatically decides whether your system is bimodal or monomodal. But most of the times when you are dealing with some sort of I would say branched polymers, or say some sort of blending polymer blends, it is always bimodal. And in case if, for example, if you are only dealing with normal polyethylene, then you can select the unimodal and then run the test. So the result you would get, one second, yeah. So the result you would get basically will be in between weight constant components and molar mass constant components, and you will get a complete distribution. Now, this data can be correlated with the GPC results, because as I have mentioned, the rheometer is very sensitive. It means especially in lower frequency regions. So here, even in case if you have some extra branch of extra branch in a polymer molecular chain, you would see some difference over in this region, in low frequency region. So this is very sensitive region for any rheometric analysis. So in addition to that, you can do multiple other tests. You can do creep tests. You can do stress relaxation. But that is something which means, like, in case if I have not discussed much about creep test and stress relaxation test, but this is also very much important characterization tools for any viscoelastic material. And in fact, with the creep test also in rheometers, you can get a complete molecular mass distribution. So there are various other tests which are definitely very much useful for various applications, like temperature dependent study, time dependent study. And in addition to that, you can also do some sort of tribology using this type of test. We can also perform tach test, tachiness, to check the tachiness of any particular sample. And we can also do some sort of penetration test. The result won't be equivalent to the penetrometer, definitely, but it can give you some idea about the consistency of your material. So if you are correlating consistency with various materials, you can do some penetration test, and penetration test will also give how the consistency varies with different samples or with different layers, you can say. So these are the tests that you can perform using a rheometer, and there are many more that you can design by your own. So with that, I would be ending my talk. And in case if you have any questions, you are most welcome to ask. Also, I would say about the question paper and the examination that we would be conducting. Mr. Mohammed Fatih will mail you individually all the question paper link. You need to click that link, appear for the exam, and start means like get your certificates automatically. So the passing criteria is 60%. If you score more than 60%, then the certificate will automatically be generated. If not, then you won't get anything. And the attempt to those examination is only one. So you can only attempt it one time. And in case, means like definitely, so that's why I would request you to appear for that examination very carefully. Appear for, means take all the questions. There are no negative markings. So if you get like 60% of marks, you will get the certificate. So with that, thank you very much. And I would like to ask you in case if you have any questions, we would be really very happy to answer.
Thank you very much, Dr. Ornov. And thank you, Dr. Fathia. Thank you, Dr. Muhammad Al-Busayfi. I was impressed, and we all are impressed by your perfect presentations and demonstrations. And I wish all of us have learned a lot from this course. And thank you, attendees, all attendees. Thank you very much for your attendance and your commitment. And please wait for the questions to be sent to you by email. And please, as Dr. Ornov said, if you have any question, please raise your hand and talk, or you type in the chat box, and we are happy to answer and help. Thank you.
I suppose there is no question yet. So we can conclude with this session. And thank you all for joining in. And hopefully you would, in case if you have any questions in future, or in case if you are doing some rheological measurement and you face some challenges, you are most welcome to contact us. And we would be very happy to answer your queries. So thank you all. Thank you for joining in, and thank you for your time.
Thank you very much indeed. Thank you.
Thank you very
Thank
much.
you very much. Thank you.
Thank you. Yeah.
Mr. Mohammed Fathi.
Yes, Dr. Muhammad.
Thank you very much indeed for this occasion, and on behalf of LBI, I would like to thank all Anton, Paar and Atef Rizk company for this nice occasion, and actually it's very fruitful for all of us, and we wish to extend this to other subjects regarding rheology or other subjects which related to any technology or equipments your company produces.
Sure, Dr. Muhammad. We have the honor to cooperate with the Libyan Petroleum Institute, and actually we all were impressed by the excessive information and in your presentations. And I'm really happy and pleased with this course achievement, and we are looking forward to cooperate with you later in other subjects in chemistry and rheology and other
Inshallah.
relevant subjects, inshallah.
Okay,
And
of
also
course,
thank
of
you
course.
very much, Dr. Fathia. You were perfect, and I'm looking forward to meet you in other events and courses.
Thank you, Dr. Mohammed,
also,
and thank you, Mr.
thank you, Dr. Arnov. Thank you very
Yeah.
much.
Thank you.
It was
It
very,
was
very
really, very
nice.
nice.
Yeah,
Yeah, yours too means
Yeah.
like you are doing a lot of research activities at your
Mhm.
facility for the crude oil. That was, I was really, it was really very good for me to understand your means like activities, what you are doing over there.
Mm.
It was really very nice and very knowledgeful,
Sure.
I would say. Yeah.
Sure, we'll extend this in the future, and we'll have many communications and emails, and maybe the chance will come one day when you can come and visit Libya and visit our center here.
Of course, it would be my pleasure.
Yeah, thank you very much indeed.
Yeah,
Thank you.
it was
Thank you
really
very
nice.
much. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.